All right, let's talk about something we experience literally every moment of our lives, but almost never actually see: sound. We're going to pull back the curtain and explore the invisible architecture that shapes everything we hear, from the quietest little room to the biggest, most incredible concert hall. Okay, let's dive right in.
I mean, you've definitely felt this before, right? How a tiny little cough can sound like a cannon blast in a dead silent library, but you can scream your lungs out at a football game, and the person next to you might not even hear you. It feels like a trick of the mind, but it's not magic. Not at all.
The answer, well, it's design. It's all about the deliberate shaping of space. There's a whole field dedicated to it, called architectural acoustics. And once you understand the basic principles, you start to see, or I guess hear, how our world is intentionally built to sound a certain way.
So, to really get this, we've got to go back to basics. What is sound anyway? Let's break down the fundamental building blocks.
Okay, first things first, sound isn't some abstract concept. It's a real physical wave of energy. It's a vibration that absolutely has to have something to travel through, whether that's the air, the water, or yeah, even the solid walls of your house. It's a tangible force that bumps into everything in its path.
And here's a wild thought. Of all the vibrations out there, our ears are only tuned to a very specific, tiny slice of that energy. We can hear from about 20 to 20,000 hertz. Now, a hertz is just a fancy way of saying vibrations per second. And that specific range, that is the sonic playground where architects and designers get to work their magic. So, our first building block is what's called frequency. And it's super simple, really. It's just how fast a sound wave is vibrating. In our daily lives, we just call this pitch. A really high frequency is a high-pitched sound, like a violin. And a low frequency is a deep, rumbly sound, like a bass drum.
And this is where the design part gets really, really cool, because different frequencies act in totally different ways. Think about deep bass sounds. They're like these big, long, powerful ocean waves. They can travel super far and literally punch right through walls. That's why in movie theaters, they have to use these thick, special absorbers to trap that bass. But high-frequency sounds, they're the opposite. They're like short, choppy little waves that bounce off of everything. So in an opera house, designers use all these curved, reflective surfaces to scatter those high notes and make sure they reach every single seat.
Okay, so frequency gives us pitch. But what about loudness? Well, that brings us to our next building block, amplitude. If frequency is how fast the wave is, amplitude is how big it is. It's the power behind the wave, which our brain hears as volume.
And right here, you can see the two sides of the acoustic design coin. On one hand, in a stadium, the goal is to amplify. They use huge, hard, reflective surfaces to make that crowd noise feel absolutely electric. On the other hand, you've got a library. The goal there is to kill sound, so they use soft, absorbent things, carpets, comfy chairs, you name it, to just soak up that sound energy and keep things peaceful.
All right, so we know what sound is. We've got pitch and we've got loudness. But what actually happens when you let a sound loose in a room? Well, it turns out it behaves in four main ways that every architect needs to master.
First up, it reflects. This is the easy one. Just like a tennis ball hitting a wall, sound waves bounce right off hard, flat surfaces. And you can use this to your advantage, like in a concert hall, to aim the sound exactly where you want it to go. Second, sound can be absorbed. The best analogy here is a sponge soaking up water. Soft, porous things like heavy curtains or those foam panels you see in studios, they just trap the sound waves and stop them dead in their tracks. Third, sound diffuses. Diffuse is just a fancy word for scatter. Imagine a sound wave hitting a really bumpy, irregular surface, like those cool geometric panels you see in a modern auditorium. The sound just shatters and goes in a million different directions. This is great because it creates a really smooth, even sound, so there are no bad seats in the house. And finally, sound diffracts. This is honestly its coolest trick. It's the ability for sound to bend around things. It's the whole reason you can hear someone talking in the next room, even when you can't see them. Architects use this in places like huge cathedrals to make sure the sound can wrap around all those giant pillars and fill up the space. So when you put all of this together, reflection, absorption, diffusion, and diffraction, you start to see that architects are basically conductors of an invisible orchestra, and a huge part of their job is to get ahead of any acoustical problems before they can even start. And in this story, these are the villains. We're talking about echoes, those really distinct, annoying, delayed sounds. Sound foci, which are these painful hot spots of volume.
dead spots where the sound just seems to vanish, and of course just general unwanted noise and way too much reverberation.
But here's the beautiful part. For every single one of those problems, there is a smart design solution. If you have an echo coming off a big, flat wall, you can just angle the wall a bit or add some absorbing panels. Done. Got a domed ceiling creating a weird, loud spot right in the middle of the room? You install diffusers to scatter that focused sound. It's like a strategic game played with physics and materials.
Now, this whole science didn't just pop up overnight. It started way back in the late 1700s as part of physics. But the real game-changing moment came in 1895. A physicist named Wallace Clement Sabine was called in to fix the horrible acoustics at a Harvard art museum. What made him a pioneer was that he was the first person to stop guessing and start measuring. He brought real science to the table. And then, when radio and movies took off in the 1920s, suddenly everybody needed an acoustics expert.
This definition really just sums it all up perfectly. It's not just about making a room sound nice. It's the whole shebang. How sound gets made, how you control it, how it moves, how we receive it, and, most importantly, how it affects us as people. So where does all this go from here? I mean, the challenges are always changing, especially because our world just keeps getting noisier and the spaces we live and work in keep changing too. The focus now is so much broader. People talk about acoustic comfort. That means designing an open-plan office where you can actually concentrate, maybe by using special sound masking systems that cancel out your neighbor's phone call. It's about designing better outdoor spaces, fighting noise pollution, reducing dangerous noise from construction and industry, and at the end of the day, it's about protecting our health and our hearing from this constant audio assault. So, I'll leave you with a little challenge. The next time you're in your office, your living room, or just walking down the street, just stop for a second and listen. Really listen. Is the sound bouncing all over the place? Is it being soaked up? Can you hear any weird echoes? Because now that you know the principles, you can start to hear the architecture.